understand. You see my first slides and you hear me, right?
Yeah, right.
Okay, good. So when I start, just let me know. I will start.
Elif Hocam.
Uh, it's up to you, Demet Hocam. I think we can start.
Okay, I can start.
Okay.
Okay.
First, yes, we will say a few words about you at the beginning of this presentation meeting. Okay, I will start now. Dear students, dear academicians, dear faculty members, participants, and I see some members of timber industry. You are all welcome. This evening, we are starting our new ArchiDesign Timber Talks series, spring semester 2023 season. This meeting is also our first meeting after 6th February earthquake caused great destruction in Kahramanmaraş. The TV earthquakes, the magnitude 7.7 and 7.6 quakes centered in Kahramanmaraş and have impacted some 13.5 million people across 10 other provinces, including Kahramanmaraş, Hatay, Gaziantep, Adıyaman, Malatya, Adana, Diyarbakır, Kilis, Osmaniye, Şanlıurfa, and Elazığ. I believe that after the earthquakes, we need to talk about the timber buildings and the resilience of them. More than before, because I already organized many events for last 15 years, and Professor Ceccotti also joined some of them as a speaker. This evening, we have a valuable guest speaker from Italy, Professor Ario Ceccotti. His speech title is Earthquake Proof Resilient Timber Buildings, the Immediate Occupancy Paradigm. Ario, welcome and thanks. Thank you very much for joining us tonight, this evening. I will try to moderate this meeting, but first I would like to introduce Professor Ceccotti briefly. He is a civil engineer who has pioneered timber engineering in Italy. As a researcher at University of Florence, he focused on wood construction structural performance since early 18th. During his tenure as a professor at the University of Venice, Faculty of Architecture, he was appointed the director of IVALSA-CNR Trees and Timber Institute, where he continued to serve until 2013, working on the ways how to valorize the use of wood in construction through new-based products like CLT and hybrid components. He was the chairman of 2010 World Conference of Timber Engineering, as he served as a member of the drafting panel of Eurocode 5, Timber Structures, and Eurocode 8, Seismic Design of Structures, NNV versions. He was a visiting professor at EPFL, Lausanne, and at UBC, Vancouver, as a visiting scientist at Forintek Laboratory in Canada. And Ceccotti initiated the way for a better understanding of the basic of timber construction for seismic behavior and design. And his work culminated with the outstanding SOFIE test conducted on the 7-story CLT building on the shaking table Kobe Laboratory in Japan in year 2007. I already shared this test with our students in our lectures many times. He has authored and co-authored more than 200 papers and 3 books, mostly on timber engineering. From September 2018 to July 2021, he was served as an invited professor professor of timber engineering at Boğaziçi University, Istanbul. I think his presentation will take 50 minutes. After the presentation, please note your questions, and after the presentation, please share your question with us. Ario, the screen is yours.
Okay, Demet, thank you very much. So I didn't think that you're going to read my CV, I would shorten it if I was imagining that. Thank you anyway. Thank you to Bahçeşehir University for the invitation. I appreciate, I am very proud of it. So my presentation is tailored for students. So academician colleagues and the scientists will pardon me some very basic things, but I think that's I mean, it was better for me to tailor the presentation for students, because students are the ones that will take care of the construction in next years. And I'm particularly happy to speak to students of a Faculty of Architecture, because somehow I am quite inclined to the Faculty of Architecture because I was professor at the University of Venice, the Faculty of Architecture, so that I know architectural students and I enjoyed my time there. So, by the way, let's go straight into my presentation. So the title is quite ambitious: Earthquake-proof resilient timber buildings, the immediate occupancy paradigm. So there are actually 3-4 points here: earthquake-proof timber buildings, 2 concepts, and resiliency, and finally the third part is immediate occupancy example. So timber buildings, earthquake-proof. So we have examples of timber buildings. They are still standing after hundreds of years in the very seismic prone regions. So that's timber buildings. The example is they behave well. In this very nice compendium of Monsieur Vieux-Champagne, you see all around the world where the global seismic hazard is very important. Yes.
We cannot see your screen. Did you start your presentation?
Yes.
We cannot see your PowerPoint now. Can you share again?
I don't know what to do. I don't know what to do. I don't know. I don't know. I don't know.
You have time, I think, no problem.
Why did it disappear? What do you see now?
Yes, we can see your presentation now.
And
that's better. We are at 5th slide, I think. Yes. Yes.
So this actually
is the second one.
The second slide. So the point is, if they pass to the full screen presentation, do you still see?
Yes, yes. This is full screen presentation. That's well. That's perfect.
Okay?
Thank you. That's okay.
Okay, I start again.
Okay. Okay. Let's go.
So I was saying there are 3-4 concepts: earthquake-proof timber buildings, resiliency, and immediate occupancy example. Do you still see my screen?
Yes, sure. Everything is okay now.
Okay, so if you are missing something, please interrupt me immediately. So that was the second slides. So we have example of timber buildings in earthquake regions, high earthquake regions. They are still standing there. In the left, it's a Turkish building. On the bottom is the concert hall in Boğaziçi University. On the right, it's 700 meters high Chinese pagoda, year 1000. So that's 1000 years old. And this was the slide of Dr. Vieux-Champagne. Can you still see my presentation?
Yes, yes.
Okay, good. So it's a very nice compendium that shows that all over the world where the seismic hazard is the biggest, and you see the red colors and brown colors, there are examples, a lot of examples of building made of wood, and they are still standing, very well behaving. And here I just underline the Turkish Himish and Badadi structures. And these few slides from Turkey, and here the Himish behave very well. And the picture on the right had been taken by Mr. Langenbach after 1999 quake, and the building is still good. And on the left, you see the signature of the quake on the first floor of this Himish structure. Is again another picture from Mr. Langenbach. Himish, very good after a quake. And this is the city of Florence. So that's my city, the city where I'm talking now. And the Dome of Florence is 600 years old. At this height, is provided by chestnut timber tie all around the entire dome. It's 600 years old. Here in Lisbon, the city of Lisbon, after the quake of 1755, half of the city was rebuilt using a combined system of timber and mortar in fields or brick in fields that is called Pombalina. And after the stucco on the central picture, there is the skeleton of Pombalina. In the USA, in Alaska, in 1964, on this house here, made with the 2x4 North American system, was intact after the quake. The only problem was the collapse of the ground below the structure, but the structure was intact after one of the biggest quake in the world. In 1906, after the San Francisco quake, this is a famous example how this 2x4 timber construction resisted well to the quake. No one was killed in this building. Unfortunately, we have other examples from the history. They are not so good. Here is 1995 Kobe quake. These two buildings are not made of wood, just concrete and steel, but you see one floor was completely missed here. So the quake was terrible. And some thousands of wooden houses collapsed on the first floor. This group of houses was 2 floors houses, and the ground floor collapsed. And you see here on the foreground, house like the ones I showed you before, and the background, they are intact houses. So some buildings behave well, others didn't. This is my favorite picture for my students that I show always I can. It's a 1989 Loma Prieta quake in San Francisco. This is Marina District. And in North America, in USA, in Canada, when you build up to 3 floors, 2x4 timber buildings, even in the very high seismic areas, you don't need an engineer, you just have to follow some descriptional standards. So these 2 buildings on the left, on the right, they are both of them 3 floors. They should have been built in the same way according to the same description code, but the left one collapsed. This is the ground floor, this is the first floor, and this is the second floor. And this other one is almost intact. How could that happen? So the lesson for my students is always the same. I mean, the same that I'm always saying the same thing. You need a good code, you need a good design in seismic regions, but you need also a good execution. If one of these is failing, something will get wrong. In this case, the execution was bad. In the left side building, instead of 3 nails per meter, they put just 1 nail per meter to save money. So, and they lost all the safety coefficients. So this was actually the result of a bad execution. So basic concept about the seismic resistance, the earthquake-proof concept, the first of our 3 points today. Before the quake, the building is intact. During the quake, there is a shaking and there is moving. There is a introduct energy to the building. The building is moving. There is a velocity. There is a kinetic energy. And after the quake, we hope that the building will still standing, maybe damaged, but still standing. So in case of wooden buildings, this may happen thanks to two different points. One point is the weight of a timber building is usually modest compared to a similar shape reinforced building is 1/3, 1/4. And the second point is the total energy input. This one at the base of the building is dissipated within the structure prior to the collapse. So point 1, when I say the weight of the building is modest, modest means everything, it means nothing. It's the point is, modest means that a wood structure is lighter than, let's say, an equivalent reinforced concrete structure. This is not a joke, actually. It's just the same building painted gray on the right-hand side, but actually can be even as dimensions similar to a concrete building. This is a timber building. This actually it's a fake of a concrete building. But the point is the ratio between the weight, the seismic weight is three times, because the weight of the building is given not only by the structure, but also by the sidings, the floors, all the HVC, everything, the people. So the ratio between the self-weight, the weight between concrete and wood is not the same ratio as the density of concrete and wood. Ratio density of concrete above the density of wood is 5 times, but in real life it comes down to 4 to 3. The second point is the totally energy input at the base of the building is dissipated during the quake. So we have dissipating energy here by connection between elements. So at the end of the quake, we have a 3-inch arch that is still standing. So the energy is dissipated at the level of mechanical connections through plastic deformation of the connections. Here they have plastic deformation, and this is the energy dissipated according to the different connections, because we have damage, internal damage, but this internal damage dissipates energy and helps the building stay standing after the building. Let's see if the movie starts. You see here, all these nails are dissipating energy, moving. All the energy is dissipated by friction with the elements. Here, in this Japanese pagoda, there are no nails, not at all. only wood. So energy is dissipated by friction, no, not by the formation of nails and the bending of the wood. So here is Indonesia. Here, the energy is dissipated by the friction between elements. So this concept of friction is being used, very newly used in New Zealand by University of Auckland. They invented a friction dissipating device that is called tectonus. This can be used to dissipate energy with no damage. So the difference between this one and this one is that the second one, actually, there is no actual damage. So this is important. So I show you these pictures here because actually this work was done by a student of mine when I was in Venice, and this student was an architecture student. So this is the north of Italy, and these are something similar to the construction we have seen before, the timber frame, and there are infills with branches, with bricks and stones. So these colleagues of yours, some years ago, a young student, very enthusiastic, built all these specimens by himself, and he tested under a force going this direction, going back. And this is the hazelnut branches and mortar. And as you see the final result and the damage. And then there is the stone. I'm not showing you the stone one, but there is also the bricks. And you see here the damages, and you see here the bricks and the hazelnut branches. So you see here the difference between the hysteresis, the energy dissipated. And also the strength is 5 times more, and also the final displacement is much bigger. So actually this is a work done by another student of mine, but this one was an engineering student, and she made a model of this, and then at the end she went to the conclusion how to have an idea how the branches one and the bricks one building made of these walls could resist a big ground acceleration of different quake. If you look at Seismic quake 1999, you see that with the bricks, you can reach, let's say, a big ground acceleration a little bit less than 0.8, with the hazelnut branches, something a little 0.2. So of course, I would say the bricks one are better than branches, but the ratio, the PGA ratio is not 5 times as the resistance, is less, because it's not only a question of resistance, it's also a question of deformability, elasticity, period of vibration, etc., etc. Why I show you, student of architecture, this test? Just because you will be asked in your career to evaluate the way how to restore an ancient structure. Engineers tend to reinforce everything. You as architects, you should keep your engineer colleagues calm and ask them to try to judge better and to make tests, because calculation per se is, in my opinion, they are not enough. You risk to over reinforce buildings they actually don't need. So the minimum intervention principle should be considered when you restore an ancient construction. So before giving the final decision, please try to make tests to understand with the help of your engineer's colleague the real behavior of this structure. So here there is a test. I suppose you don't hear the noise. So you hear my voice only, and you see this is a test done in 2005 in a 2-story Japanese system timber construction in the NIED laboratory in Miki, Japan. So sorry. So at the end of the first, 2005, this is the first test. And you see the building is moving. You see some damages here. But the building actually is resisting. So just let's check me. Do you hear my voice? Hello?
Yes, we can hear you. No problem.
Okay, you have seen the movie?
Yeah.
Yes, sorry, because actually I must confess you, I actually I didn't I wasn't able anymore to give lectures online with my student at Boğaziçi. It's always very tiring to me. I don't see anyone. I speak to myself. Sorry about that. I need some comfort. I mean, to need some confirmation from you that you are seeing what I'm showing you. So, oh, I'm sorry. So Japanese actually they are doing like this. When they have something new, they make a test. So, and this house was actually according to the new regulations, and the company built this prototype. They came to NIED, they make this test in order to show this house was capable to resist a big quake, I mean, the design quake, and it resisted. But as researchers, so the results was satisfying. Everyone applauded at the end of this test. Everyone was happy because this means earthquake proof. So the lives are protected. No one would have been dead in this building. But as researchers, they continued the test without any intervention. And this is the second test. This is year 2000. And this is the quake, the 1995 quake of Kobe. Of course, this one actually is a little frightening, but this building is still standing. And now we have the third quake in a row. And now, okay. So, as I said, this test was successful. Everyone was happy because human life was protected. The same concept we have in cars, in our cars. This is a famous example of Formula One Grand Prix, and the pilot is safe. The car must be wasted, but doesn't matter. The human life is protected. So the concept of earthquake-proof timber buildings is that human lives are protected. But in Eurocode 8, of course, in your Turkish standards, Turkish seismic design standards, that is one of the most advanced standards in the world, the Turkish one, there are several levels of, let's say, safety. The first level is the one I show you now. I spend these first minutes just talking about this. Human lives are protected. But there is also consider the possibility of other buildings. So the so-called strategic buildings that must remain operational after the design quake. So it's made a difference between the ordinary buildings and the strategic buildings. There is a difference in the quake. So the design level of these two classes of buildings is different. That means the strategic buildings can be designed, can resist such a large quake without any important damage, but of course they will cost much more than building ordinary buildings like houses. So in Eurocode 8, it was invented a so-called importance coefficient, GAM I, important coefficient GAM I. So GAM I for the ordinary buildings is 1, and GAM I for the strategic building is 1.4 or 1.5, like was. So what is the point? You increase the design action of the quake. Look at this. So this ends my first part presentation. Now we are going to the second, resiliency. In year 2011, a big quake hit the city of Christchurch in New Zealand. And you see here from this aerial view, apparently, this is different, but this, apparently you don't see so many damage. But what was the problem? The problem was that all these buildings, they were actually abiding the rule of saving lives. No one died on the Grand Chancellor Hotel. But the point is that this hotel was really damaged. No collapse, but heavily damaged. And it was decided that reinforcing was actually impossible, and they decided to demolish it. And they start demolishing it from floor by floor coming down. It will cost a lot of money. So you must know that in New Zealand, almost all the buildings are insured against the quakes. So that means that if the quake comes, the insurance companies must reimburse their clients. And the case of New Zealand, the point was that insurance company would take around 40 years to pay off the cost of the Canterbury earthquake. 40 years. So they risk to bankrupt, actually. So in order to avoid a similar situation, so the point is, they had casualties, of course, but a lot of buildings were just need to be demolished. So the point is, under the pressure of insurers, the point is that we should think, since now then, to design for buildings, even the regular buildings, if they are not strategic building, to design them as more or less strategic building. So the point is this is the formula that in Eurocode 5 is used to consider the design shear earthquake action at the base of the building to increase this quantity by the coefficient gamma I. So in fact, in year 2017, at the World Conference in Chile, this word resilience started to appear. And the resilience was considered a new challenge in earthquake engineering. So the present seismic design criteria of safety of life, requesting that buildings do not collapse, must be replaced by codes that allow cities to continue operating in a few days. And this is a consequence of an ability to evacuate millions of people of mega city. There is also a point of actually making the, as I said before, the insurance companies to work profitably, with no bankrupt. So this word resilience, this is in psychology, but we are in construction field. So the resilience means the ability to bounce or spring back into shape position. So, and the afterquake immediate occupancy concept brings us to the last part of my presentation, the immediate occupancy example paradigm. I like this picture that I took from Professor Costantiniu, University of Buffalo professor, during a lecture he gave with Professor Ilke a few weeks ago. So these are the strategic building. Of course, we may not say we want to build every single house as strategic building, but there is a concept between life safety and operational. There is a concept of immediate occupancy. Immediate occupancy building is safe to occupy, but possibly not useful until cleanup and repair has occurred. So let's say clean up and some repair, but the important point is people can immediately re-enter the building. Maybe building is not perfect, but maybe we need some adjustment, but still occupable. So, and regarding the wooden constructions, in this point, because actually my presentation is about wooden constructions, so I show you the example of a cross-laminated timber. I'm getting short of time, I see, so I'm sorry, I'm going a little bit faster. So, and this product was invented and tested at the end of year 2000 at the University of Graz. Those panels are coming in big or small dimensions. They can be worked very precise way with the precision 1 millimeter. They are connected with self-tapping screws and plate connectors. So you may build actually a very rigid and stable building made of those panels connected by nails, screws, and connectors in a very efficient way. And the way of construction is very fast. And in Italy, year 2000, this was the first medium rise, 7-story CLT building. But at the University of Graz, no one checked the CLT buildings against seismic, earthquakes and seismic actions. So this was done in Italy with Progetto SOFIE, and we started testing single walls, and then 1 floor, and then 3 floors. And you see the testing on one wall, you see the hysteresis loops. At the beginning, we thought that because these panels are very rigid, the energy, dissipating of energy wasn't actually very much. Instead, the real life, we detected that energy dissipated here, it can be important. In this building, we made a total of 26 tests, and 14 of them were more than 0.5 G of peak ground acceleration. So this was the first, this is 2006. You remember the movie, the Japanese movie, 2005. So when when we went to Japan to test this building, actually, I must confess you, I was thinking this building sooner or later would collapse like the other a year before, but it was impossible to make this building to collapse. So this is the real GA Kobe, the one that did destruct the building before. And this was all. And a lot of tests. At the end, we gave a 1.2 G quake, and the only damage was here, few nails broken, but the building was still standing very straight. So the year later, 2008, so we tested a 7-story building. And this you see arrangement of the connections. And that building was designed according to Eurocode 5, Eurocode 8. By the way, Eurocode 5 and Eurocode 8 are translated into Turkish language. So if you ask to TS office, you can have them. As a student, I think you should have them free of charge. I don't know, but ask your professor. So these are some testing on the preliminary testing on those in the walls of these beams. This all down here was invented and designed by us. And you see here is the screws are more resistant than the bolt. Some pictures taken during the erection of the building. And these are 3 tests. This is just one direction. Look, it takes a few minutes because there was counting from the speaker. It's coming. So this is testing 1. One direction. And now we have testing 2. This is a Kobe. So and this is the third one. This is another quake, Kashiwazaki 3D. These are a little bit less impressive, but if you look at the ground floor, is actually the movement are impressive. So what is the point here? That after 3 quakes, I mean, more than 3 quakes, actually, after, let's say, 22 tests, not all of them, they were quake, they are just step testing. But this is the test 1, this is the test 2, and this is the test 3 that I show you the movie. So after all these tests, actually this one, everyone is multiplied by 1.15 because of the design, but doesn't matter that. So after also this quake, the building, this was before, this was after. If you remember the movie of 2005 on the 2-story Japanese building was completely different. After 3 tests, it was destroyed. So I must say that since then, there is no more test on timber buildings that will achieve the collapse, but everyone wants to test resilience, so that want to show that their buildings are resilient. Here, what does mean, let's say, immediate occupancy? If you look under short direction, the frequency of the building after all the tests more or less remain the same. We had a reducing of the frequency on the strong direction, but actually you can live on this building without any problem. The building is a little more deformable, but is still capable to host people. Okay. This is this is good. I mean, in this way, we can say the CLT buildings are very good for immediate occupancy construction. But I want to show you something like this, because you may ask yourself, but if this building remains, let's say, elastic, okay, we have energy dissipated, but the building actually remains mainly elastic. So that means that we have, from the bottom to the top, we have an amplification of the acceleration at the bottom. At the bottom, we had 1g. On the top, we had 2g. So 2g is not very much, but it's still important. You see the table and etc. So the idea is a further step. The idea could be to use base isolation, and let's say, you know, this is the same building of 2005 that before the test I show you later. And but in this case, look at here. If you look at here, and if you look at here, it's in the bottom here there are isolators. There are isolators. You see? You see, this is the pictures taken from below, and you see how it works. So in this case, you can actually build house, like my friend, actually was even my former student, built. It's made of, you see the man here, right? This is the man. So it's a very simple 2-story house that he wanted to build on seismic isolators. I think is not really is not necessary for such small building. But in case of let's say strategic buildings like this one, for example, and that has been designed and is under construction from Professor Nuti, University of Rome, and you see these buildings are on seismic isolators, and you see they are moving. So in this case, actually, you can guarantee that the content of your building is safe, and because the amplification of the base P ground acceleration is not doesn't reach the building. So why I'm showing you this point? The point is that timber construction, you can build the resilient building, immediate occupancy building for residential purposes without seismic isolation. But if you go to important buildings or the buildings whose the content is important, you may use base isolation. And the cost is not actually very big. The cost is affordable. The two-story CLT building I show you was just actually an exercise by enthusiastic colleague that was very keen on timber structures. And finally, just a comparison between the SOFIE building that I showed you before and an equivalent concrete building, reinforced concrete building, designed for immediate occupancy, like this building here, the SOFIE building. This building here was designed by colleagues. They are from Bozici and from IETU. They are experts on concrete. So please consider this comparison is, let's say, not biased. It's actually honest comparison. So so these two buildings are equivalent, and the colleague studied several designs, and at the end they designed the most economical reinforced concrete building for immediate occupancy. And of course, I would say the environmental cost, I mean, in terms of, let's say, carbon footprint, is in favor. It's in favor of CLT building. The cost in terms of carbon emission is much lighter than on CLT. But of course, this was actually very well anticipated. In Turkey, on the contrary, the cost of today, the cost, the reinforced concrete building, the economic cost for the client will be much less if concrete than CLT. But in the future, who knows? But what I'm trying to underline always that we can make a calculation of an economical cost difference, not based on the absolute cost, but made on some relative cost. So what is the concept? The concept is, what is the difference, the increase of cost between a normal building, that means designed for life safety, and an immediate occupancy design building? So if you have CLT, the increase of cost, in this case, from normal to resilient building in CLT the quantity of timber is still the same because you can't put less timber than that one. Instead, regarding fasteners and connectors, you have a 7% increase. If you have reinforced concrete from a life-safe design building to a resilient building, you must, I mean, in this case, the increase of concrete was 13%. The increase of steel bars was almost 30%. So this means, I think this actually, it's interesting. So as a civil engineer, I'm not used to say that I am passionate of timber. I admit that. I have a passion for timber, but I wouldn't say that timber is the best material. I always say that the engineer, the architect should choose the material according to the building that must be designed. But if it doesn't know timber, it will never choose timber. So that my point to my colleagues is try to teach timber in your universities. By the way, I can say that the target of resilience with the wood is reachable at very competitive costs. So this is the final slides. We are in University of San Diego, University of California, San Diego, USA. I think in a few days, they will start testing this 10-story CLT building. It's a little bit more complicated, the one that I show you, but of course, it's 15 years later. Our test was in 2007, this is 2023, and this test, of course, is open windows, it's open, it's much, much advanced. It's very, very ambitious. So, and the test will last a few months actually, because they will test with according to different situation, etc. And I am sure that will use sooner or later some dissipator, friction dissipator at the bottom. I don't know if they will use the one I show you, because the one I show you are the New Zealander ones, but maybe some friction dissipators. So, okay, I finished. I am 3 minutes late. Okay, that's not bad.
Ario, thank you very much for your presentation. It was really informative for all of us, I think. Elif Hocam, maybe we can take questions now. Because we have good information about shaking table tests during the last 15 years. It started in 2006 in Japan with your studies, and now we hear in the last news you are working on another high-rise timber structure which will made in CLT.
The Metanem. I'm not working there.
Okay,
no,
okay.
No.
You get information for us.
Too much.
Okay. Okay.
Too much. I'm retired.
Okay.
But I will attend that test. Sunday I will attend the test, I'm sure. Yeah.
Okay. Okay. Is there any question for our guest? Elif Hocam, maybe can ask some.
So
I should.
This is not a question. This is always because the students are shy. It takes always a little bit more time.
Yes, I know.
Okay.
I know.
This
But
is not a.
How can I see you instead of my slides? I don't know.
Me?
No, I mean, yeah. Okay, good. I see you now.
Okay.
Good.
But maybe if you can close your presentation, it's easier. You have done more space on screen, maybe. I'm not sure, but if you can stop sharing the screen.
I see you. I see the mat. I stop sharing. And I hope
Okay,
if
okay.
some question is about my slides, I can
Okay,
be able
okay,
to
okay.
resume
Yes,
the
you are
slides. I
correct.
am
Okay.
sure.
In Turkey, because you have been in Istanbul and you know this is always the same topic. I'm just asking this. In Istanbul, it was like that also traditionally. So it is burning, then massive materials, then earthquake, then timber. It was always such a change.
I
Um,
remember that.
I know you are a structural engineer and you are more dealing with earthquake, but really, I don't know how we can take this feeling of being somehow very uncertain about timber and the issue that it burns and so on. Are you also facing such questions within Italy, Europe, and whatever, also in Japan?
So the the question about fire, it's another, let's
Yeah,
say,
yes, I know,
presentation. So
I
that's
know that.
if you want, I mean, I have
Just
good
okay.
professor that can make another presentation on this. But the point is, in the modern structures, at least in Italy, even if we know that the time of burning of wood can be under control because you know the velocity, etc., 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 you can calculate the fire resistance. So that means the time from starting of the fire and the collapse of the structure. You can control everything. You have the fire brigades standards that ask you for 30 minutes, 60 minutes, 90 minutes, 120 minutes. You can reach even 3 hours. That's okay. And Italy, usually we don't use sprinklers as they do in North America, for example. But for to me, if you ask me to design a structure, I would prefer to protect my timber inside. And the way we protect, and this is usual, it's the usual way in Italy. If you say, if the fire brigades ask you for 60 minutes fire resistance, you cover your CLT with a layer of gypsum plaster boards that will collapse after 60 minutes. So the point is, the idea is, but it's not written anywhere. It's just, I mean, see, a sensible thing to make, to encapsulate your wood. In the famous Brock Commons building at UBC in Vancouver, the picture you see, all of them are showing beautiful timber, everything is light wood colored, everything. But at the end, now you don't see anything inside, because apart some walls, because everything is covered by gypsum wallboards. It's called encapsulated structure. And I think this is very sensible. So we are actually designers, we must protect life. So I wouldn't save money just saving on protection of wood. No matter if you can control the burning of the wood. This is my modest opinion, my personal opinion.
Yes, thank you, thank you.
Maybe one wall you can, let's say, take one wall made of wood or one floor, but not the entire. These tall buildings, oh, you must be careful. But I'm not an expert on fire, so
Yes,
you should ask other guys.
yes, yes. Okay, okay. Thank you very much. Okay, dear students, do you have questions?
At my architectural students in Venice, I was teaching statics.
Mm-hmm.
I wasn't teaching timber structures. I was teaching statics and strength of materials. That's no. But anyway, that's if they have questions, they always can write me. Demet knows my email, so that
Yes.
that's okay. That's no
Okay.
worrying.
Okay.
No questions.
No questions. Okay.
Everything was
As
very
usual.
clear.
I don't know that because the first part of my presentation was very slow, and at the end, when I realized to be late, I start
No.
running. That's maybe they are two different pace. Sorry about that.
There's no question here, I think. Okay. If you want, you can write your question to chat box.
Ahmet Hocam.
Ahmet Hocam. Yes.
And Taha Karim. Okay.
Ahmet Hocam.
I think
Yes.
the students should go first. I just was the sort of the infill. Let them speak first, I think.
Okay. Taha, yes, please ask your question.
Hocam, my question is about like, let's say, rules for government. I've been in Turkey like a year, but as a regular, let's say, construction work, I couldn't see like the like things that you should that you show us in presentation. Let's say the reducer for earthquakes. It's like a machine, like you put it in the construction, it will like reduce the earthquake effect. Why like we couldn't like see something like that, yani? I mean, to like to protect people, to make our construction work like more safety, like our building more safety, we should use the like these things to reduce earthquake effects. Why we couldn't see something like that in construction work? Actually, that's my question.
So you, if I understand well, you ask me why in Turkey these systems are not so used?
It's not about Turkey. Even in my country, in my own country, they don't use it. I see many videos from Japan actually. They use it, and the earthquakes there, it's achieved to like, I don't know, maybe 9 degree on measurements Richter, yani. I mean, there is no any damage, there is no demolishing, but in here we see like a lot of even it's like 7 or 6 degree of earthquakes, it will like destroy buildings.
My answer is I don't know. I don't know. That's the point is always economic. I mean, most times is an economic issue. So more or less, it's an additional cost, and I don't think it's just something that professionals they don't know, because in universities everywhere in the world there are people, they are experts. Even in your country there are people that are experts on this, so that must just find the good people. And even this system can be even used or adopted for restoration of existing buildings, but in that case they are much more costly. So I'm sorry, I'm just a researcher. I'm not good in economics. Sorry about that.
Thank you.
Let's say, for example, in Italy, after the quake in 2009, an entire city was rebuilt, And all those buildings, no matter if they were made of steel, wood, and concrete, all of them were built on seismic isolators with new foundations. But if the cost of the building was, let's say, 1,500 per square meter, 1,500 euros, 1,500 euros per square meter, the cost of the foundations and the basement of concrete and the isolators was again 1,500. So the cost was double. So I don't know. That's I don't know. It's something that has to do with economics, with politics. Sorry about that.
Okay, thank you, Ario. Ahmet Hocam, maybe you can ask your question now.
I have many questions. This is a very eye-opening presentation. Thanks very much for this. In the case of fire, I was thinking that the CLT would perform quite well because of its sheer thickness. But when I look at the last slide, which is going to be tested, apparently certain lightness, actually this is I would almost call this a frame structure with shear walls. Is that what we should call it then in the case of the UCSD testing?
I agree.
So that's going to be very interesting to see the results. I wish they could also perform some fire tests on this. This could be a groundbreaking.
I would suggest them.
That would be interesting to see the comparisons after the tests, of course. That was one thing, because these are worries we have about timber in Turkey, fire, obviously, but also the looming danger, or the almost certain case of earthquake, especially in the Marmara region again, near Istanbul, is really it's almost like a trap. We're in it because it's the building stock is out there. We're all sitting in those buildings, and there is no way of reversing this in the near future. We can, when we build new, of course, we can always observe these codes. We will, and give more importance to timber, hopefully. But what do we do now with the existing ones? That is something that's sort of going through my head all the time. And now that you mentioned the isolators, I experienced something in the construction of the Atatürk Airport. At that time, the new airport, at the turn of the millennium. The earthquake, 1999 earthquake, occurred and caused damage, or basically cracks at the connection to the columns of the main roof system, the steel roof system. And they, after the completion of the construction, they went ahead and re-isolated the roof structure from the columns, the concrete columns. This was a very major operation where they reinforced the columns with extra, because they were concrete columns. They reinforced the columns with another, almost a layer of concrete, and isolated one by one to insert the isolators. Now, when I think about that, when I think about these tall buildings in this last project, I was thinking, is it maybe at the sheer cost? I mean, the cost could be enormous, but would that not be possible to go into this practice of inserting isolators in the, let's see, in the basements of existing buildings. Now, this is of course not about timber, but when you just mentioned this, it just occurred to me, maybe that could be a way out for the immediate future of the building stock that we have. That would be a big investment, but might be worth it. And how technically that is possible for 5-story buildings, obviously, is another question. But I think, I mean, many buildings have been jacked up, especially historic buildings of stone in some cases. So why not? Maybe that is a possibility. What do you think?
This could be an idea.
Yeah.
Yeah.
I think this is out of
Yes, of course.
is it a crazy idea, or is it a possibility? I don't know. If it were all wood, if they were all wood like they used to be, that would be wonderful. That would be very easy to check them out.
With Professor Ilki and Professor Lush, we were talking, but at the end we stopped because I went back home using CLT panels for let's say reinforcing substandard reinforced concrete frames.
Oh, great! Yes, why not?
Taking away the bricks on the external parts. The bricks are falling down and make those walls made of CLT, and how to connect the CLT walls to the timber, to the columns and beam. Would have been something to investigate. And of course, it depends about the quality of the concrete, etc., etc. Well, it was a very interesting idea, but that didn't go through. That's unfortunate.
Absolutely,
But we have done some theoretical investigations with master thesis of students of ours, and the results are this system could be helpful for very bad buildings. If I mean, not so good concrete or very strange shape, but very well designed reinforced concrete building. The increase of strength, let's say, is 20-30%, but they are badly designed is 50-60%. I mean, the peak ground acceleration will go up. So that's, of course, it's a matter of working at this. This could be an idea for your students.
No, maybe you could again regroup here and suggest it to the municipality. I think they would be welcoming this kind of insertion with timber. That would be wonderful. I think the light material, and that could have a future. I think we're desperate for any kind of idea, but this is a sound one. It's a good one. So why not pursue it?
Okay, Ahmet Hocam, thank you very much.
Thanks very much.
Thank you.
I think there's no question from our side, and the time is up. Thank you very much for your presentation, Ario. And we have a little tradition here in ArchiDesign Timber Talks as Bahçeşehir University Faculty of Architecture and Design. We donate in our guest name. A donation has been made in your name to SAY Foundation, helping underprivileged children for equality in education. I will send this to you with the email. Okay.
Thank you.
You're welcome. And
That's
thank
nice.
you.
That's
Yeah.
nice.
Thank you
That's
so much for all your time and for your sharing your experience with us, with our students and academicians. Thank you very much. Thank you very much.
Thank you. I appreciate it. Thank you. Ciao.
See you.
Ciao. Ciao.
Thank you.
Bye-bye.
Bye.